Hello everyone. In this problem, we are going to look at a combination of impacts in particles as well as rigid body kinematics. So here, assume that you have a 2 degree of freedom planar arm, and it is playing ping pong with you. So the gripper at the end effector is holding the ping pong racket rigidly, firmly, and everything is happening in the XY plane. The ping pong ball is moving toward the rocket, and when angle Q1 is 30 degrees and Q2 is 45 degrees with length of L1 equal to 1 meter and L2 equal to 0.8 meter, you can definitely determine the location of the end effector, right? So here, if you want to find the location of this red point, you can definitely find that. Now also, you have to consider the distance from the point that the impact is happening to this end effector, to the very bottom of the end effector. So this distance also, if we assume the ball is going to hit right there, this distance from here to here, also, if you might want to call it L3 or anything, this distance L3 is also given to you as 0.2 meters. So this is also 0.2 meters. So basically you can extend member number 2 to be L2 plus 0.2, which is going to make it also 1 meter. And now this point of impact or contact here, you can find the velocity of it because you know the configuration of the system, the robot, which is Q1, Q2, L1, L2, and I also have given you the angular velocities of link 1 and link 2. They are 3 radians per second and 1 radians per second. So I also know Q1 dot and Q2 dot, right? So they are both also, or omega 1 and omega 2, they are both also given to me as positive numbers, which means counterclockwise, if we use traditional XY, which we are using here. And so definitely you can find the velocity of this contact point. And now the mass of the rocket is given as 150 grams. The mass of the ball is given as 20 grams. E is given, the coefficient of restitution, as 0.8. The velocity of the ball is given right before the impact. It is 2I minus 5J, right when it hits the rocket. You want to find the velocity of the ball right after impact, okay? And one other thing here is you can neglect the effect of the impact on the velocity of the rocket. So let me add that for you here because it is important. So we should neglect the change in velocity of the rocket due to impact because the ball is not really heavy and the rocket is rigidly kept in place by the manipulator, which are typically rigid objects, okay? They are stiff objects with big masses, and you can assume that the change in velocity of the rocket due to impact can be neglected. So velocity of the rocket after impact is whatever it is before impact. So now with all that info, you want to find out what is the velocity of the rocket after impact, right? Or if you have a system in place that can give you velocity of the rocket after impact, right? So if you have any sensing device, any LiDAR, radar, any camera that can estimate accurately the velocity of the ball before and then after impact, somebody might ask you, what is the coefficient of restitution E, right? So let's say this mechanism is used to, for example, this system is used to estimate the coefficient of restitution. Okay, so if we want to solve this problem, first thing first is I need to find the velocity of the rocket, at least the point of impact of it, correct? So if I call this point here, the point of impact, point P, I need to find velocity of point P, which is like the end effector but extended for extra 0.2 meters, correct? And if you know from, I don't want to get into robotics because this is a dynamics problem. So all we need to do is to write coordinate of point P in terms of theta 1 and theta 2 or Q1 and Q2 and then take time derivative to relate it to the dots, okay? So what we do here is we say x of point P is clearly L1 times cosine of Q1 plus L2 times cosine of Q1 plus Q2, correct? Right? Because this portion here is L1 cosine Q1, and then this portion here that you have to add, this is L2, but cosine of the angle that the second link makes with respect to the x-axis, so you need this angle here. And this angle is clearly Q1 plus Q2, right? Because this smaller angle here, this one, is Q1. So you have Q1 plus Q2. The absolute angle of link number 2 is Q1 plus Q2 because Q2 is a relative angle. It's from the extension of link 2 to the extension of link 1. So the absolute angle of link 2 is sum of the two angles. So that's L2 cosine of Q1 plus Q2. This is L1 cosine of Q1. And similarly, you can do a similar thing for y of point P. Y of point P is going to be L1 sine of Q1 plus L2 sine of Q1 plus Q2. So these are the coordinates of the impact points, x and y of P. And now if I want to find the velocity of it, all I need to do is to take time derivative from these equations. Right? In robotics, we can do it through what we call Jacobian. But here, let's just go ahead and derive it. I can show you what Jacobian is. So here, if I take time derivative, it's going to be x dot of P, or velocity of P in the x direction. It is equal to, you take a time derivative, pay attention, this is a Q1, so you're not taking Q1 derivative, you're taking time derivative. So it's going to be derivative of this one with respect to Q1, which is negative L1 sine of Q1. But because you're taking time derivative, you have to multiply it by Q1 dot, correct? That's chain rule. And then similarly here, this is going to be negative L2 sine of the summation. And then times the derivative of the term inside sine, which is Q1 dot plus what? Q2 dot. Similarly, y dot of P is going to be L1 cosine of Q1 times Q1 dot, and then plus L2 cosine of Q1 plus Q2 times Q1 dot plus Q2 dot. Okay, if you want, you can rearrange it and write it this way. You can write it as x dot P and y dot P to be a matrix times Q1 dot and Q2 dot. And this matrix is going to be, you have to factor out Q1 dot in the formula and Q2 dot. So if you factor out Q1 dot, you see you have negative L1 sine Q1, negative L2 sine Q1 plus 2. So this is going to be negative L1 sine of Q1, negative L2 sine of Q1 plus Q2. Okay, this is your first element, which is the coefficient of Q1 dot, and then you can add the second element, which is the coefficient of Q dot, and that is simply negative L2 sine of Q1 plus Q2, and then do the same thing on the bottom, factor out q1 dot, you will get L1 cosine of q1 plus L2 cosine of q1 plus q2. And then the coefficient for q2 dot is simply L2 cosine of the summation of the angles. Okay, so basically this is the velocity of point P. And this is the vector of joint velocities. Okay, you might call it vector q dot. So this is the end effector velocity or the impact point velocity. This is the joint velocity. And this matrix in robotics that connects these two together, we call it what? We call it Jacobian, J. Okay, just learn that Jacobian, it's not just robotics. You learn it probably in your calculus too. It's a matrix that here you can multiply by the joint velocities to get what? To get the end effector velocity or to get the contact point velocity. But if you see, I have all of the numbers here, right? This J, which is a function of Q1 and Q2, I have the angles for it. I have L1, I have L2, Q1 dot and Q2 dot. The only thing here is this L2 here should not really be L2. This L2 is the modified L2. So if you really want to modify that, instead of the L2, wherever you see L2, you have to say what? L2 plus 0.2, because as I told you, there is an extra 0.2 between the impact point and the end effector. So if you want to use the L2 that is given to you, 0.8, the number that you have to use here is 1 meter. Okay, so all you need to do is to change that to L2 plus 0.2 to find the velocity of the impact point, not just the end effector. Okay, and now it should be easy to plug in all of the numbers we have, because we have the Q1s, Q2, L1, L2, and the Q dots. So if we go ahead and plug in all the numbers, here I'm going to do it in MATLAB and get you the numbers for you. So here I plug them into MATLAB, and the numbers I get is Vx of the impact point is negative 5.36 and Vy of it is 3.63. Does it make sense? Yes, because this velocity means negative x and positive y, so it should be something like in this direction. And based on the motion that you see here, that both members are doing counterclockwise, then the impact point is moving like this, which is absolutely right. So definitely the number makes sense. Now that I know the velocity of the impact point before impact, I can say this is also the same as what? Velocity of the impact point after impact, right? Because I said neglect the change in velocity of the rocket due to impact. So this number that I found, this vector, is the velocity of the contact point or the rocket at the contact point, both before and after impact. So right now I'll concentrate all of my rocket at the impact point and consider it like a particle. Okay, so I consider my rocket like a particle at the impact point, which has this much of velocity before and after. The mass over there is 150 grams. The mass of the ball is 20 grams. The velocity of the ball before impact is 2 I minus j. What I need to find is velocity of the ball after impact. So if now we have done the kinematics of rigid body, now we need to do the impact between the particles. So here I write it again. V of the ball is equal to 2I minus 5j. Before impact, velocity of the rocket or the contact point P is the same as whatever it is before impact. After impact, they are the same number, and that is negative 536 and 363, correct? As we can see here. And E is 0.8. What we need is velocity of the ball after impact. And here prime means after impact, without prime means before impact. Okay, so this is definitely an oblique impact. It's not a head-on collision because I have two objects. One of them is like this. One of them is the rocket concentrated at point P. And this is M of the ball. This is M of that rocket at point P. They are coming at each other, but if you look at their velocities, they are not collinear, right? This is the ratio. If you look, it's 2.5. The ratio here is negative and it's less than 1 of y over x. So definitely the direction of motion is, the direction of motion for both objects is not on the same line. So it's not direct central impact, it's oblique impact. And now the problem is you need to find the place that these two will touch each other, so you can find the plane of contact and the line of impact, and that comes from the normal to link Q2, correct? Because when they touch each other, the common tangent is the rocket and the common normal is normal to the rocket. Well, the rocket is aligned with link number 2. And link number 2, as you know, the angle of it, I said, is Q1 plus Q2. At the moment, Q1 plus Q2 is 30 plus 45, so it's 75 degrees. So this is the surface of the rocket. The ball comes and hits here. So the line of the common tangent is at 75 degrees, and the common normal is normal to this in this direction. And so if you want the angle of this plane here, that is clearly 90 plus 75 degrees, which is 165, right? So now along this line, the components of the velocities would change, but along the other line, the components of the velocity will not change, right? So here, for example, you can call this one the x-axis, and y is going to be the common tangent. It doesn't matter which direction, up or down, if we want to go with the system that we know. So we go downward like this. So now this common tangent is y, and that common normal is x. Along x, the components would change based on the conservation of angular linear momentum for the whole system and the coefficient of restitution. In the y direction, nothing would change. So we have to decompose the velocities of point P and the ball along what? X and Y, and see which one is changing, which one is not. Well, the rocket, if you look at the rocket has what? The rocket has these components, negative 536 and 363. Is that aligned with X or Y? Probably not, because as I said, this whole angle is 165 degrees. And if we find the cosine and the sine for 165, or the tangent of 165, right, it can tell us whether any of the velocities are in line with it or not, which shouldn't be. So tangent d of 165 is that ratio, right? And that 3.63 divided by 5.36 is definitely not that ratio, correct? So you see that it is definitely not aligned with that, and the ratio of 2 and 5, which we had for the velocity of the ball, is also not aligned. So definitely none of them is aligned, okay? That's what we have. Now let's go ahead and get the unit vector of that direction. So cosine d of 165 is this much, and then sine d of this is this much. So negative 97, if we use 2 decimals, negative 97 and 26. Negative 97 and 26. So this will give us the unit vector in the x direction, right? And then if I want the unit vector for the y direction, I can find that one as well. And then I can project each one of those vectors, v ball and vp, along these x and y. So this is what I might call u of x, correct? Or your new I, basically based on the old I, based on the traditional I, 1 and 0. So if I call it like this, and then for u of y, this is going to be what? So the angle of y is another extra 90 degrees on the top of 165. So if you look at the angle of y, it's that one plus 90 degrees, which is going to be 255 degrees. And if I look at the sine of 255 and cosine of 255, right? They should be similar to these guys except for exchange because I'm adding 90 degrees. So 255, you see, it has what? The sine of it is the cosine of the other one, and the cosine of it should definitely be what? Negative as well, because it's in the third quadrant, right? So the sine and cosine should be exchanged, but both negative. So sine is going to be negative 0.97, and sine is going to be negative 0.26. So these are the unit vectors along which I need to project my V ball and V of the contact point. So let's go ahead and copy these. So we can use them down here for our impact problem. Okay, so here we go. So as we said, along the X, the forces exchange. Along the Y, nothing is going to change, right? Good. So let's calculate the Y component of the ball, which is not going to change. So what I need is to project this guy along the Y. See what component I will get, and that component is not going to change. So what is it going to be? Well, how do I project a velocity along a unit vector? You know, we use dot product. So the VB y component, and if you don't like calling these x and y because we use these original ones x and y, what we can do is to call these x prime and y prime. Okay, so I can call them x prime and y prime, and here I can give them a different name so that we don't confuse them with x and y. So here we go. So VBY prime, okay, which is the velocity of B in the y prime direction before impact, it's going to be the same as whatever it is after impact, B prime of B in the y prime direction, and that is equal to VB dot UY prime. So let's go ahead and dot product this vector with that one. And here we can use the command dot in MATLAB. So what is dot of basically negative what? 2 and negative 5, correct? 2 and negative 5, and the other vector was sign was negative, correct? Negative 97. Well, actually, it looks like it's 97. We want to use two decimals, not 96, 97 and 26. Okay, so 97 and negative well, wait a minute, let me make sure. Yes, but the unit vector is cosine in the I and negative and sine in the J, so I have to exchange. Okay, so there's going to be this much. Okay, it's cosine I plus sine J. So if we want to put it in order, we have to do it this way. And the answer is 4.33. Okay, it is 4.33 meters per second. Does this make sense? Always check. So your velocity is like this, 2i minus 5j, so it's to the right and downward, so it's like this, something like this, right? That's v of b. Now this v of b, if you decompose it along x and y, you will get a component like this and a component like that, correct? The component along y prime should be positive, and the component along x prime should be what? Negative. So you see, because this one is positive, you probably done it right. I can also find the x component of velocity of the ball along the x prime direction, which is going to be v of the ball dot ux prime, using a dot product, and let's do that one here. So for that one, it is going to be the same, except that the cosine component, if you looked at it, the cosine of 165 is negative, and the sine of it was positive. So we have to do like this, correct? And you see it is negative number, negative 3.24, and we expected it to be negative, so it is completely fine. There we go. So these are the components of velocity of the ball along x prime and y prime. Now this one is not going to change, so we found it already. We found that this component of it is not going to change. This x prime component does change based on the coefficient of restitution. Definition of coefficient of restitution is E is negative of relative velocity after impact to relative velocity before impact, but in the direction of what? Line of impact, which is x prime here. So it should be something like v prime of b, correct? X prime minus v prime of p x prime divided by v of b x prime minus v of p x prime, correct? These v's that don't have prime are before impact. The ones that have prime, they are after impact. So negative relative velocity after to relative velocity before. Now my unknown here is this guy, v of b after impact, this one. V of b before impact, I found it. I have the number here. This is negative 3.24. What about the rocket, or point P? How much is the x component of velocity of the rocket along x prime? Well, for that, I need to what? I need to now project this vector along x prime. So I also need velocity prime of P along x prime, correct? Which is the same as velocity of P along x prime, because the velocity of a rocket does not change due to impact, and that is the dot product of this vector and x prime. So I need to use x prime, and I need to use that negative 5.36. So I use the same unit vector, but this time I use that negative 536 and 363. Correct? And if I do that, I get 6.14. So the component of velocity of the rocket along x prime is 6.14, and again that's right, because the rocket was moving, the point P was moving in such a thing, negative I positive j, so it was moving like this. And of course, when you project that along x prime, you will get a positive component. So now I have both of these numbers. Both of these guys are 614. And my E is 0.8. So the combination can give me velocity of the ball after impact along x prime, right? If we calculate it. So here I calculated it, and the number is v prime b in the x prime is 1364, and in the y prime it is 4.33. So if I want to write velocity of the ball after impact, it is going to be 13.64 times u prime x, ux prime, sorry, and then plus 4.33 in the uy prime. And if you want, you can replace ux prime and uy prime from whatever they were. So if you bring these guys right down here and plug them here and here, it can give you velocity of the ball along the original coordinate frame. Correct? So here I do that for you. And here I have calculated it and show you the final result. So the final result is this much. This is the velocity of the ball after impact, negative 13I plus 1.58 J, which means the ball is going to go back big time along X and small along Y. So it is going to go something like this. When it hits, it's going to go back this way. And that is kind of expected. Right? So hopefully now you can analyze what's happening when your 2 degree of freedom robot is playing tennis, ping pong, whatever game. And here we did everything in 2D. So this is a very good combination of kinematics for rigid bodies and kinetics, or impact in this case, for particles, right? So hopefully it was useful to you. Now, in general, if we cannot neglect the effect of the change in velocity of the rocket due to the impact, then you have to do more computations, right? You have to look at where the centroid of the rocket is and everything. But here, to make life easier, we assume something that we can do calculations fast. Thank you so much. I will see you in the next example.